Okay.
Excellent. Splendid. Well, thank you very much for inviting me. Sorry I'm not there in person. But yeah, 11 years, it has been far too long because it's always great talking to you. This is a little different, as Phil has suggested. My background is in astrophysics. I drifted into education. I drifted from there into public engagement, all of it still involving astrophysics. And now I'm kind of doing lots of very different things. Some of them involving the crossover between astronomy and art. And I just wanted to talk to you a little bit about that, why I got involved in it, why I think it's important, and why, most importantly, I think it's fun. But I'm going to start with this quote from Charles Snow, CP Snow, back in 1959, when he was asked to come up with a report for the government about the clash between the so-called two cultures, the arts and the physical sciences. And he came to the conclusion that there was a distinct problem with the way people approach these two. And in particular, the way that the idea that somebody was literate and educated was dominated by the arts. Whereas if, as he says in this quote, you went up to a random person in the street and asked them, what was mass, what is acceleration? Nobody would be upset if they didn't know the answer. But if they went up and said, can you read? Who is Shakespeare? People would be upset. And he felt that wasn't appropriate. And there was this clash between these two cultures. And my starting point for a lot of this stuff is looking at this clash and seeing whether it really exists. And if so, what we can do to try and heal the divide between the two. And so what I'm going to be looking at this evening is science and art together. And I've divided this essentially into three groups of things. Science helping art, art helping science, and then ideally, can we find some way of doing the two together so that they're mutually supporting each other? And maybe we could call that culture, for want of a better term. And I think the picture in the background here is quite indicative of this. This is a beautiful painting by Joseph Wright of Derby about the time of the formation of the Royal Society. And this is the scientist. He's not a real scientist. He's a sort of traveling showman, but he's demonstrating the air pump. And this is a very big thing at the time. The air pump had just been invented, and they could take these glass jars and pump most of the air out to create a near vacuum. And the idea was you'd take this, you'd travel around with it, and you'd put a bird inside your glass jar, and you'd pump the air out, and the bird would fall unconscious. You can see the children down there are quite upset by this. And if you got your timing right, you could put the air back in and the bird would come back to life. But it didn't always work, and sometimes the bird just died. And so it wasn't necessarily the most ethical approach to entertainment, but it was a way in which science and art were starting to come together. But that wasn't the first time. Science and art have been together for a very long time. And in particular, the technology that science creates has been very important to the development of art, more so than a lot of art historians would like to believe. There's a kind of culture in art history, not exclusively, but a lot of art historians have this view that all progress in art is driven by artists of genius. And that is often true, but a lot of them couldn't do that, couldn't make that progress without the technology to support them. And a good example of this is optics. The camera obscura, which is a simple piece of optics, a single lens, has been used for quite a long time by painters to make their job easier. You can take your dark box with its lens in one side, and you could project an image of what you want to paint upside down onto your canvas and just sketch it. So you're not doing that difficult thing of trying to sketch by switching between viewpoints. It's just there in front of you. And some, including people like Hockney, have argued that this has been around for a very long time, prior to the Renaissance. And it's common sense. If you're an artist at that period, you make money and have a living by producing as much art as possible as quickly as possible. That's how it works. And if this is going to quarter the time it takes you to do your initial sketch, then it's insane. You'd be insane not to. But you want to keep it secret. You don't want to advertise that you're doing this because it takes away some of the mystique of what you do. But there is evidence that this was happening quite early on. This is a lovely painting by Lorenzo Lotto of husband and wife. I don't think we know who the husband and wife were, but it's from 1523, early 1500s. And it's a fairly classic painting of the time. Nice use of shadow, nice use of texture on the cloth. But the most interesting bit for me, and for Hockney, who came up with this, is this part of the cloth below. Now that looks like quite a nice, simple piece of perspective. Got a nice sense of depth from the pattern on the cloth disappearing into the distance. But if you measure that perspective very accurately, you discover there's two bits of perspective. If you take the lines from the front part of the cloth, they go off to one vanishing point. But if you move a little bit further back, you get a different vanishing point. Now, Lotte was a very good artist. He wouldn't have done that by just being incompetent. What's far more likely is that he was using a camera obscura, because the lenses they had then were not very high quality. They couldn't make them very large. And so the field of view, the depth of the field of view was very small. So the depth that things stayed in focus. So you couldn't just set up your camera obscura and sketch the whole thing. What you had to do was set it up so that the front of the cloth was in focus, and then adjust it a little bit once you sketch the front, and the next bit of the cloth would be in focus, and so on. And every time you do that, you move the vanishing point slightly. In fact, you move it by exactly the amount you would expect to see here. So this is evidence, not conclusive proof, but strong evidence that even as early as the early 1500s, artists were using the available technology to make their life easier. And they were able to produce paintings more quickly and more accurately than they'd been able to before. And so the technology is helping the artist to do what they want. The science is helping the artist. Some examples are a little bit more subtle. This is an early watercolor by Turner, painting of some waterfalls on the Clyde. Beautiful watercolor, but very much of its time. This wasn't radically different to the kind of watercolors that everybody else was producing at the time. But then something happened. Then a new kind of paper was produced. Now, prior to this new paper, if your paper got too wet, it would disintegrate. And so you couldn't get very soggy paper, and you had to paint your watercolors very quickly. You had to do it with relatively dry paint. But with this new paper that had been developed, you could soak the entire sheet of paper and it would stay firm. And so you could have this very wet paper and you could paint on top of it. And that allowed you to create much more expressive and flowing watercolors. And this is the kind of thing that Turner started doing as soon as he was able to get hold of this paper. We have evidence that he did buy this paper. And it's much more flowing. It's much more what we would now perhaps call impressionistic. And there's a paper historian, and that really is a job. There's a paper historian called Peter Bauer, who's made the argument that without this new paper, not only would Turner not have been able to create these new watercolors, but he wouldn't have been able to explore this new style of expressionist paintings, not expressionist in terms of the school of art, but just producing an expression of what he wanted to do on the paper. And that would then mean that without this step from the simple traditional watercolors to these more flowing, expressive ones, he wouldn't have been able to produce things like this. He wouldn't have been able to use these famous oils of things like the slave ship and the famous ones that you see on calendars all over the world. Now, I'm not saying this is conclusive proof, but it is quite persuasive. And so Peter Bauer is arguing that it wasn't just this one artist of genius. Yes, you needed the artist of genius to make this step forward, this leap forward, but he wouldn't have been able to do it without the improvement in the technology. It was the science that made it possible for Turner to express his genius in this way. And so that relationship between science, technology, and art is one that has been going on for a very long time. And it's becoming even more obvious now. You get artists who just create things inside computers entirely and so on. And so there is a growing relationship between scientists and technologists and artists. And this is something that I started getting involved with quite a long time ago now, it must be about 15 years, when an artist called Andrew Small got hold of me. And he was producing a sculpture to go at the end of a coast-to-coast walk. So this is going on the eastern end of a long coast-to-coast cycle path, in fact. And he was doing various artworks along this. And he wanted the one at the end to relate to the surroundings. And in particular, he wanted it to relate to this little white lighthouse you can see there. And he wanted it to relate to the time of the lighthouse as well. And he discovered that at the time the lighthouse was built, there was an alignment with a particular moment when the sun sets. So on a particular day, I think it was the solstice, the sun sets so that it appears to just rest on the top of that lighthouse from one particular point. What Andrew wanted to do was create this large sculpture with a viewing point where you could look through and see the sun apparently balance on the top of this, must be sunrise, not sunset. Anyway, you see the sun apparently balance on the top of this lighthouse as the sun begins to rise. And what he wanted was the constellations marked on the sculpture in the right places for that moment in time. And he couldn't do the calculations himself, but that's what he wanted. So I got together with him and we chatted a while and I came up with the calculations. And you can just about see marked on his sculpture there are the names and patterns of various constellations. Now, unfortunately, this particular moment was also related to a time in history with Hereward the Wake, I believe it was, in that area. And so it wasn't just any old solstice. It had to be a solstice when it fell on a particular day at a particular time of the century. And that only happens once every 100 years. And this photograph was taken at that exact moment in the 21st century. And as you can see, it was incredibly cloudy. So this is a little disappointing for him, but nevertheless, he was very excited about the idea of bringing the science, bringing the astronomy into this. And I didn't do very much. I just put some numbers into a computer and printed some things out for him. But it meant that he could be confident that the art was producing what he wanted it to. And I did that. That was an afternoon's work, and I went and got on with my real job. But I began to think a little bit more about this, and I began to think about how there might be other ways of exploring science, exploring astronomy with artists. And I've been thinking about this for a while when I went to the theatre. As Phil mentions, I'm a big fan of theatre, and I went to see a company called Unlimited, who do wonderfully strange small-scale theatre, often involving a bit of science. They do a superb play about time travel, and another one about quantum entanglement and so on. So they really like to get into their science. And I got chatting in the bar afterwards with the director, a guy called John Spooner, who's fantastic. And he was telling me about his new project, which was going to do their first play for children. And he wanted it to be inspiring. He wanted them to get the children to think about what they could do with their lives and how they could be ambitious and imagine an exciting future for themselves. And what he always wanted to do when he was little was go into space. And so what he was going to do was he was going to write a play about going to Mars. And that's what he did, but he needed some technical help. And so he got myself and a couple of other scientists involved to provide support, advice, and basically fact-checking for this play. The play was produced, it toured around the country, it was incredibly successful, and it really did do the job of getting kids enthusiastic about their possible futures. To give you an idea, the play starts with the astronaut on the left here, sitting on the front of the stage and opening an envelope. And it's the day before he launches to go to Mars, the first human mission to Mars. And on the front of the envelope, it says, to be opened by me the day before I go to Mars. This is a letter he wrote to himself when he was 10. And he's opening this letter and he's talking about the ambitions he had when he was a 10-year-old. And of course, the audience is full of 10-year-olds who have those ambitions. And he was basically saying, well, it came true for me, it could come true for you. So it was a fantastic production. We got some very enthusiastic audiences, but we also went a little bit further. As well as having the play, after a lot of the performances, there was a panel, a discussion panel for the kids and their parents to just ask questions. This kid had a lot of questions, very enthusiastic. This was in Leeds. And this was the panel. And to me, this is one of the most interesting things about this project, because normally, I don't know how many of you go to the theatre regularly, but if you go to the theatre and there's a panel at the end, it's the cast and the director. You don't get anybody else there. This panel has the director, that's John there, just speaking, who's also the writer. But you've got me as an astronomer. You've got this gentleman whose name I've forgotten, who's a social worker. You've got a primary school teacher. You've got the woman here who actually runs the engagement program for the theatre. And you've got Gail sitting near the middle there. Gail is awesome. She, like many people when she was young, wanted to go into space. But unlike a lot of people, she didn't have any of the advantages that you need to do that. She basically had to leave school when she was 16, didn't have any qualifications. There was no realistic chance of her going into space, but she still wanted to. So while she was working in a supermarket checkout, basically, in the evenings, she did an open university degree, got her degree in physics. And then she did a part-time PhD, again, while holding down a day job. And while she was going through her PhD, she applied to the astronaut training program at ESA. And they were so impressed with her that she got into the final 10, which is absolutely incredible. Now, she wasn't the one that was chosen. Tim Peake was the one who was chosen, but they liked what she did so much, they did hire her. They hired her to run their microgravity training program. So she may not have been into space, but she has trained astronauts who have. but she still wants to go into space. She now runs a nuclear physics laboratory in Australia, but she's still looking at ways that she can get her ambition to go into space. And so this is from somebody who was forced to leave school at 16 and is now a very successful physicist with an ambition to go into space. And having her there telling her story to these 10, 11, 12-year-olds was fantastic. And that panel, I think, says a lot about how this kind of thing, this way of bringing the science and the art together, can reach people in a way that just talking about science can't. They can get excited. There was noises, there was sound, there was special effects, there was smoke, there was possible disasters, there was all sorts of things going on in this play, but all of it was about the ambition and the excitement of these two people realizing their dream of going to Mars. And maybe they weren't in touch, maybe they didn't make it. The ending is ambiguous. You don't know whether they landed successfully or not. And that's a question that the kids have to answer for themselves. But the excitement was there. Now, we're very proud of this, but it was also pleasing that other people thought it was good as well, because we got some awards. And again, it's always very nice to get awards, but I think the interesting thing about these is the variety of the awards. There's a charity award for arts and humanities. There's an award for space education, and then there's an award for women in science and engineering. And it's very rare that one thing could tick important boxes for all those three areas. So doing this was great fun and very stimulating, but it also showed me the possibilities of using art as a way to bring the excitement of what we do, the excitement of astronomy, the excitement of science and engineering and technology to a wider audience than you would normally be able to. So that's, in a sense, the science helping the art, but it's also a little bit of the art helping the science, but I'll come back to that in a minute. The other way, of course, that the science helps art is just providing inspiration. So far I've been talking about technical assistance, but we can inspire, and this is especially true of astronomy. People are fascinated by space. You all know this, but if you go out and talk to a random person in a pub and start talking about black holes, they will almost certainly be interested. There's that sense of awe, there's that sense of wonder. We've got enormous scales, we've got long time scales. Most importantly, we've got questions that haven't been answered yet, important questions. Is there other life out there? How did the universe begin? What's going to happen in the future? All of these fundamental questions that we haven't answered, which keeps it exciting. And of course, as far as artists are concerned, it's visually stunning. This is a Hubble Space Telescope image, part of a star-forming region. And I just chose this one because it had sort of aesthetic similarities to the Turner painting I showed. Obviously, they're not the same sort of thing, but you can see how artists might be inspired by these extraordinary images. So there's lots of different ways in which science can help the artist to create the art that they want to create, technologically, advice, and through inspiration. Now, the other way around is a little rarer. There are examples of this where art has helped science, but they're not as common. At least they don't appear to be common. Maybe they're just less obvious. I mean, there are some examples. Leonardo da Vinci is an obvious one, but he wasn't really an artist or a scientist. He was an everything. So maybe these things it's a little harder to do. And that's something I want to come back to later, because I think we're missing an important trick here. I think scientists could learn a lot from working more closely with artists. But there is one area, and it's the area that I specialize in, where art and science are very close and where art can have a strong effect. And that's not just science, it's science communication. Now, in astronomy, we have an easy job with science communication because people like astronomy. Talk about space, people are interested. You start talking about nuclear physics and people lose interest very quickly. I don't understand why. I find them equally interesting, but people do. And there's evidence to support this, particularly in schools. There's been some surveys done. This is one from the year 2000, but there's been several done since, which show quite clearly that the only area of science that doesn't have this drop-off in interest as the kids get older is astronomy. And it doesn't seem to matter whether you're male, female, what your social background is, what your ethnic background is, there is this continuing interest. And so from my point of view, that's obviously nice because I'm trying to share astronomy, but it's also an opportunity, and it's the opportunity to use that fascination to get a better appreciation of all of science. I'm not particularly interested as a science communicator in getting people more interested in astronomy because I don't need to. What I'm interested in doing is going to people and say, well, yeah, okay, you like astronomy, but why do you like it? And when they start thinking about why they like it, the reasons why they like it are often it's because it's scientific. It's because it's about answering questions. It's because it's about exploring unknowns. It's because it's about extreme things happening. And so can we use that interest and fascination with astronomy to get a better appreciation of science? And this is not just because I'm a scientist and I think everybody else should be. I do, but that's not the main reason. I think this is because this is going to be an increasingly important aspect of our lives. Science dominates everything we do. There's absolutely no doubt about that. Every single thing you do every day, you do because of the science and the technology that underpins it. Even if you're going for a walk, you are dominated by the science that takes you there. It might be in your shoes, it might be in the air you're breathing, it might be in the view around you. There is science, there is technology. But a lot of people are not just not understanding that science, but are frightened of it. And being frightened of the thing that runs your world is not a good situation to be in. And a lot of that fear comes from a lack of understanding, from a lack of appreciation of how science really works. It's not this magic wand which comes up with solutions. It's a process which allows us to reduce our ignorance. And when people understand that, they are less scared of science and they can appreciate more what it can and, more importantly, what it can't do. So this is an important thing to do. This is something that I think it's well worth spending a large fraction of my life on, because if I can make a difference to people about how they appreciate science, I'm making their lives better. Sounds very noble when I put it like that, but it's also great fun, which is the main reason. Now, there's an important rule in all science communication. I call it preaching to the unconverted. If you want to talk to people who are not already interested, they're not going to come to you, because why would they bother? They've got other things to do. If you want to talk to people who are not already interested, you have to go to them. And this may seem like an obvious thing to say, but it's surprisingly difficult to do. And one of the ways you can do it is by just literally going to people where they are. Find situations where the people you want to share with are already busy or already engaged. And one of those, of course, is the street, shopping centres, places like that. So a number of years ago, I got together with a group of street theatre experts, and we came up with something called the Science Butlers. This grew out from a weird performance that the butlers and myself did in the Edinburgh Fringe every year, where we would dress up as butlers. You can see Fletcher the butler here. And we would go out onto the streets of Edinburgh and offer our services completely free to anybody who wanted a butler. It was a very weird way to spend a week, but it was great fun. The Science Butlers were an extension of that. We would take the persona of the butlers, because butlers are very safe. Butlers are there to serve you. They're not challenging. They're there to help you. And so we could take that safe, friendly, slightly amusing persona of the butlers, and we could do science with them. So each butler, and there were half a dozen of them, had their own tea trolley. And on that tea trolley, they had the kind of things that a butler would have. Fletcher, for example, was preparing breakfast. So he has eggs and he has cereals and things like that. And then he would take those and he would do science experiments and tricks on the street. This was the streets of Liverpool. This is just around the corner from the cavern, in fact. And it was incredibly successful. And our first performance in in Liverpool, in one day, the butlers performed to something like 5,000 people. They were absolutely shattered at the end of it, but they got a huge amount of feedback from people, and a huge amount of conversations about the nature of science. So it was a very successful thing. Unfortunately, we had to disband the Science Butlers in the end because we didn't have anywhere to keep the shopping trolleys. Fletcher had them in his living room, but then he moved to a smaller house and that was it. So the Science Butlers only lasted a couple of years, but they showed me the power of taking an art form that already engages with people, in this case, street theatre, and just putting science in it, using the science as a new kind of performance. And so I began looking for opportunities to do this, not just in places like the street, but anywhere where people are coming along for a different experience, often an artistic experience, and where I can introduce them to science. And I ended up with my own exhibition at the Tate in Liverpool, which is a slightly bizarre experience. I had a 6 weeks residence at the Tate in Liverpool, showing people some of the science that we're doing, exploring the research that we're doing, but also bringing that into the way different cultures have reacted to the night sky, just through things like the names that they gave the constellations. For example, there's one constellation, and it's only a sub part of the larger Western constellations, but there's a constellation which in China is called the Group of Seven Incompetent Thieves. And as soon as you know that, you want to know the story. You want to know the culture that leads to that. You want to know what was so incompetent about them. I never did find out. I'm still trying to work out why they're called the Group of Seven Incompetent Thieves, but it led to great conversations. And that wasn't the same group of people who we talked to in the shopping center, but it was a group of people who were not there to experience science. They were there to explore art. But we still had conversations with them about the nature of science. Another example was a dance company I worked with called IJAD. They got in touch with me because the choreographer, Jumana, was very interested in the way gravity acts through dancers' bodies. This was partly because she was just interested in the way it creates movement, but also because of a health issue. Dancers injure themselves a lot. Very hard to believe the facts, but at the time we were doing this, 1/3 of all young dancers were injured and couldn't work. They had knee injuries, they had other joints that were injured. It's an incredibly big problem. And a lot of it is because when they're taught to dance, they're taught the movements they're supposed to make, but they're not taught how gravity is acting against some of those movements. And so Jumana thought that if we could get some way of exploring the nature of gravity, center of gravity, center of mass, how it works and so on, then that might help dancers to control their movements in a way that means that they will damage themselves less. And she's been doing a bit of work in this for a while, and it does seem to work, but she wanted to explore gravity a little bit further. And so we started working with a small group of dancers and just looking at gravity. And in particular, we started looking at orbits. And so we had demonstrations like this. This is just a simulation of two objects orbiting around each other in space. And it's very simple and it repeats, and the dancers were able to get together in pairs and they could reproduce these movements and they could understand the concept of center of mass and so on. It was great fun. But then one of the dancers said, well, look, there's an odd number of us here. Can not three of us do this together? I said, well, no, that's not going to happen. That's far too complicated. But it's only one more. So we went away and we did another simulation of the three-body problem. And suddenly it's not so simple. It doesn't repeat. It goes chaotic. And this idea fascinated them. Now, as a physicist, I'm used to the idea that even a small increase in the complexity of a problem could produce a huge increase in the complexity of an answer. That's chaos theory. But I'd never really come across it in this form. And the idea that they couldn't reproduce these movements and there was no way that three dancers could work together like this in a sensible way got them very excited. And so we started to produce a performance based around the complexity of orbits. And Jumana took that away and said, well, okay, I don't just want this to be a dance piece. I want this to help other people understand gravity and orbits. And so they created a piece which was partly workshop and partly dance. And it started with people coming in and being given various balances. There was a swivel balance, a sort of an ordinary seesaw that you can see down there, and then a circular one, and bits of paper that they could screw into balls and try and balance. And to start with, most people could balance two things on the seesaw, but as soon as you had a third one on that swivel, on the round one, nobody could do it. They would be falling off. They would be putting one on and it would roll into the center. It was a mess. And then after that initial workshop, they would go into another room and there'd be a dance. And this is one of the dancers here rehearsing. And everybody wouldn't just be watching this dance. They would be part of it. They might be a planet. They might be a star. But they would be given instructions about how to move. Nothing complicated. The dancers were doing most of the movement, but just helping to balance out the orbits of the two or three dancers. And after about 10 minutes of doing this and playing around and listening to the music and working with the dancers, the instructions became gradually more and more complicated. And people were doing more and more sophisticated things to balance out all the different orbits until it got to the end when there was just a simple instruction out of the loudspeakers, which was balance the room. And every single time, suddenly you had a room of 30, 40 people all arranging themselves so that they were perfectly balanced. And then one of the dancers would move, and if a couple of other people would move to compensate, and they had this room completely balanced. They understood the way that the gravity was working. They then went out and repeated the workshop, and they, as you can see, no problem balancing 4 or 5 things on that swivel. So doing the dance, being involved in the dance, helped them to understand the gravity and the way the orbits worked far more than if they'd just been taught. So it's a very great fun, but a very successful way, again, of exploring the science through the art. So having done that sort of thing and worked with a few artists, we began to get a bit ambitious. And one of the first things we did for getting ambitious is make a garden. This was a show garden for the Royal Horticultural Show at Tatton, not too far from you there. Because in 2013, the theme was galaxy. And my boss, then Mike Bode, his neighbours designed gardens. Dorrie was a former English teacher who retired and started working on gardens, and her son Howard is an architect who has also got an interest in gardens. They decided they wanted to do a garden for the RHS show in 2013. And so they began to talk to Mike about how they could bring galaxy into this. This is the design of their garden, and this is the reality of it. Beautiful thing, nice spiral structure showing the spiral shape of a galaxy, but it had a lot more to it than that. Even things like the tarmac that you can see, I'll just show another picture of that. The tarmac at the bottom here is not normal tarmac. It's made of rubber, and so it's bouncy. And the idea was this part of the galaxy is relatively sparse, there's less mass in it, and so the gravity would be weaker and you would feel bouncy. There were different colored plants to represent star forming or non-star forming regions. There was even in the center this water feature which had water disappearing into it rather than coming out of it, because it's a black hole, and that's what happens with black holes. So every feature had something to do with the galaxy. And what we did, myself, Mike, a couple of our colleagues, stood in the middle of this garden for a week and talked to people. So they'd come in and they'd say, well, what's this garden all about? And we'd explain the different bits and pieces. And we'd talk to them about black holes, and we'd talk to them about star formation and spiral structures. And it was great because nobody was there to talk about the universe. They were there to talk about plants. But they had no choice because they couldn't get past us. And so they ended up talking about the universe, and it was very popular. We got a lot of very positive feedback. However, it was very hard work, very tiring. At the end of the week, there were 5 of us sitting in a tent. It just started raining. There was mud everywhere. We were about to start dismantling the garden, and we said, that was great, but we are never doing this again. It would kill us if we tried to do this again. The next day, Mike phoned me and said, what about Chelsea? And so we decided to try and do a garden at Chelsea. And this time, Howard, who was leading the design, got really ambitious because he felt galaxy was too obvious. The spiral shape was very nice, but as soon as you think of galaxy, you think of a spiral shape. And he wanted to do something a bit more challenging. So we spent a couple of evenings just chatting together over a few drinks. And we eventually came across the idea of dark matter, and Howard began to get very excited because here was something that we didn't understand, which probably existed, but we weren't absolutely certain, and that you couldn't see. And he thought that would make a great thing to make a garden about. And so we began to explore dark matter in a little bit more detail. And we started, again, talking about gravity. Many of you will recognize this diagram. This is the kind of thing we were showing Howard. So this is the planets and the speed that they orbit around the sun. So we've got Mercury, Venus, Earth, Mars, and so on. And this is the measurements. We put the line for the theory, and it goes through the points. So this is Newtonian gravity. This is the inverse square law. This is what Kepler was able to demonstrate. And we understand this. We've understood it for a long time. And the observations and the theory match perfectly. So that's all nice and simple. Nothing very exciting about that. Now, when you look at a galaxy, it's going to be a little bit more complicated because in the solar system, all of the mass is in the middle. It's where the sun is. The planets just don't count. In a galaxy, the mass is spread out a lot more, so the gravity is going to be a little bit more complicated. But we can still calculate what we think it should be. And the most important thing is when you start getting a long way away, when you start getting outside the visible galaxy, you expect the speed to drop. May not drop in exactly the same way as it does in the solar system, but you expect the speed to drop. So basically, you expect something a little bit like this. It may not be this exact shape, but they'll be fast towards the middle and slow in the outskirts. What we measure is not that. This is a a graph showing the speed of objects orbiting around a galaxy. Now, in the middle, it goes a bit strange. And that's essentially because it's not purely gravitational. There's a lot more, there's some slightly more complicated things going on in there. But once you get away from the center, essentially the speed doesn't change. And that doesn't make sense. We know that the further away you are from something, the weaker the gravity is, and therefore the slower you go. So how can this be happening? And there's only two possibilities. Either we've got gravity wrong, which doesn't seem very likely because it works very well everywhere else, or there's lots of stuff we can't see, and it's spread out a lot more evenly than the stars. It goes out much further than the stars do. And so when this was discovered, people said, well, if this stuff exists, we can't detect it, must be a different kind of matter. Let's call it dark matter. And for a while, that was the main piece of evidence. And then other things started coming along, things like this. This is a beautiful image from the Hubble Space Telescope of a cluster of galaxies called Abell 2218. And you can see lots of the galaxies here, these sort of orange fuzzy things and the bluish fuzzy things. They're all the galaxies in the cluster. But you can also see these weird streaks. There's a red streak there and some blue streaks and some odd distorted things. And they're all over this. And they're not in the cluster. They're galaxies that are much further away than the cluster. And they look weird and distorted, not because they physically are, but because the gravity of the cluster is bending the light from those distant galaxies, called gravitational lensing. So what you're basically doing is the gravity of the cluster is producing something that's a little bit like the bobbly glass that you sometimes get in people's windows. And when you look through it, everything becomes distorted. And from that, these pictures with all these different arc-shaped galaxies and so on, you can work out essentially what the bobbly glass looks like, which means you're getting a map of all the gravity. And you can compare that with all the stuff, the stars, the gas, and so on, and there isn't enough. There's nowhere near enough to produce the sort of gravity that you see, and it's spread out differently. Again, there's a lot of stuff we can't see, and it's not in the same place as the stars. And we see this not just within individual clusters, but through the entire universe. This is a kind of model, a simulation, a sketch, if you like, of how light travels from the very early universe, the cosmic microwave background, which is basically the first light in the universe to become completely free, how that travels through the universe, being bent by the gravity of clusters of galaxies, and then it arrives with us. This is what something like the Planck satellite sees, and it can measure these distortions. And so this is more evidence, again, that there's a lot of mass out there that we can't see and isn't in the same place as the stars. And so we talked to Howard about all of this sort of thing, and he got very excited, particularly about this. And he went away and he came up with a design for a garden, which has all of these features in it. This is now flipped. So this end here, where we've got that kind of light area, that's a light box. That's the beginning of the universe. That's the cosmic microwave background. At the other end, we have us now. And so between there, we've got the entire history of the universe. We've got iron bars showing how the light moves. We've got all sorts of other things as well. It's great. This is the actual garden itself at the Chelsea Flower Show. And every single feature of this garden has something to do with dark matter. The choice of plants, sometimes because of their names, sometimes because of the shapes that they form. The bent iron bars, even things like the bamboo. There's a lot of bamboo in this. And when you're there, even in the slightest breeze, that bamboo is moving. It's drifting and moving around. Now, you can't see wind, but you know it's there because you can see the bamboo moving. And that's an analogy to dark matter. We can't detect the dark matter, but we know it's there because of the effect it has on the light passing through it. And so there were all these different features. We set up the garden. We had all these lovely bits and pieces there. And then we prepared to spend a week standing talking to people again. But before you do that, you have the prizes. Now, again, like the awards we got for the Mission to Mars Theatre Group, prizes are nice. But here they're a bit more than nice, because if you can get a gold or a silver medal or a silver gilt medal here at the Chelsea Flower Show, everybody wants to come and see your garden. There's a lot of gardens at the Chelsea Flower Show. You can't necessarily go to all of them in a day. But if you've got a medal, everybody wants to come and see yours. And so we were really hoping that we'd get a silver or a silver gilt medal or something like that. We didn't think we'd get anything like a gold, because you don't get gold medals the first time you demonstrate, but we did. Our first garden ever at the Chelsea Flower Show, and that's Howard in the middle looking very pleased. That's about as pleased as Howard will ever look, because we got the gold medal. And that meant that everybody was going to come and see our garden, and we'd be able to talk to tens, even hundreds of thousands of people. And then it got even more exciting because we got the best in show. There's 3 categories at the Chelsea Flower Show, and we got the best in show for our category, the fresh, which are the sort of experimental and imaginative gardens. And that means that not just everybody at the show wants to come and see your garden, but everybody who knows anything about Chelsea wants to know about your garden. And so we were absolutely swamped. We had television there every day. It was the only garden that appeared in every single broadcast of Gardener's World. And to me, this picture in the bottom left here is conclusive proof that we won Chelsea, because some of you may recognize that's Maggie Aderin-Pocock from Sky at Night fame. And she was asked by the BBC to come in to the Chelsea Flower Show to explain dark matter to the people coming to watch Gardener's World. And that is, to me, exactly the purpose of science communication. It's talking to people about exciting things that they're not expecting. And so we had a fantastic week. And the numbers, I still can't quite believe we were this successful. I mean, we physically talked to about 14,000 people. This is having conversations. Again, at the end of the week, quite tired. We know there's about 160,000 people at the show. Most of them came to the garden. A lot of them took leaflets and shared things on social media. We had articles in the national newspapers and around the world. Lost count of the number of radio interviews that we did. And the official figures for the TV audience for the slots about the garden were over 200 million people around the world. So this is 200 million people around the world turning on a program to learn about plants and finding out about the universe. I'm very proud of that. Now, we haven't done anything this insane since. I'm looking for some ideas at the moment. We haven't done anything this insane since because, frankly, it nearly killed us. But it does show the power that bringing science and art together can achieve. But I still only talked about the first 2 of my ideas. What I want to do finally is talk about something where I'm working with a friend to try and bring science and art together, mutually supporting each other. So it's not science helping art or art helping science, it's art and science coming together to create something new. The person I'm working with is a composer called Gavin Starks, who runs an organization called DGen. I've known him for 30 years or more. I taught him when he was an undergraduate. And he's interested in using astronomy to explore sound as a compositional tool. And I'm interested in using sound to explore astronomical data. And the challenge, of course, is that although most of what we know about the universe comes from different kinds of light, I mean, there's a little bit of gravitational waves and particles and so on, but basically most of what we know comes from different kinds of light. A lot of that light is not visible light. It's X-rays, it's gamma rays, it's radio waves, all of these different kinds of things. And so as soon as you try and visualize this data, you have to adapt it. This image here is not what the eye would see, even with a giant telescope, because you've got X-rays colored blue, you've got optical light colored green, and you've got radio light covered red. And no one telescope can see all of that. We have to bring it together. Now we can do that, but maybe there's another way of exploring this data. Maybe we can use sound, because sound has its own advantages. We have a much better sense of spectrum with sound. If you think about the nature of light, the bit of the electromagnetic spectrum that we can actually see is a tiny fraction of it. If you could imagine the electromagnetic spectrum as a piano keyboard, where the bit that we can see, visible light, is 1 octave on that piano keyboard. So, you know, the C to C, 1 octave on a piano keyboard. Then in order to fit all of the rest of the electromagnetic spectrum that we've observed, you would need a piano keyboard larger than the distance between here and the moon. That's how little of it we're actually seeing. But we can hear many more octaves of sound. The disadvantage of sound is our positional resolution is dreadful. I look at this picture and I can see individual pixels. If this would sound, I would know roughly what side of the room it was on. So our positional resolution is poor, but our ability to hear ranges of spectrum, high pitch, low pitch, is very, very good. And people have been exploring this for a number of years. And one of the simplest things you can do is a thing called sonification, which is taking data and turning it into sound. A classic example is pulsars. And with a bit of luck, when I show you this, you will hear the sound of a pulsar. So this is taking the radio signal and just turning it directly into sound. Can somebody wave or let me know if you can hear that? Could you all hear that okay? People on Zoom can. Could people hear that in the hall?
Andy, can you hear me?
Yep.
Yeah, we heard that perfectly.
Excellent, good, because the next one's more important. That's just an annoying noise. I'm going to play it again because it's an annoying noise and I like playing annoying noises. So that's what a pulsar would sound like if you could hear it. And different pulsars spin at different speeds. So some of them are higher pitched and some of them are lower pitched. And so you can listen to a pulsar and hear a little bit about it. Now that's, as I say, people have been doing this for a long time. It's quite an interesting way to explore one kind of object. But Gavin and I got talking and we felt that there was more that you could do with this. And in particular, telescopes were starting to be developed, which produced things called data cubes. Now, normally, when you're taking a measurement with a professional telescope, you've got a choice between taking an image, so you get a picture, maybe with some colors, but you get a picture, or you can take a spectrum of one object, which is where you take the light from that object and split it out into all the colors. So you know how much of each different shade of red, each different shade of green, and so on. And usually you have a choice. But modern instruments, particularly in the radio, can do both at the same time. You can get an image, but behind every pixel on that image, you have an entire spectrum. Now, we can't see that all in one go. What you end up with is basically a colored picture, but it doesn't show all the detail. So we came up with the idea of taking one of these so-called data cubes, turning it into an image, but having it so that as you moved your mouse around the image, it would take the spectrum behind that pixel, turn it into a sound. So red light is low pitched, blue light is high pitched, and play it back to you. And this is just a movie of that happening. So you can see as the mouse moves around, it picks up different spectra. Red bits are low pitched. And then if you go to a blue bit, which you should do in a second, it becomes much higher pitched. I'm going to stop that because the noise gets a bit annoying after a while. So you can use this to explore the data, and things which look the same color can sound quite different because the color can be produced by slightly different spectra. So I was interested in this as a way of exploring the data, but Gavin just wanted it as a new instrument. So he's been actually composing using this galaxy. This is an observation from the ALMA radio telescope. And I'm currently working on a new version of this where we'll be able to take any part of the sky from a giant survey, take that, pull out a data cube and use that bit of the sky as an instrument. It's going to take me a little while because it's quite complicated, but I'm getting there with that. So we're going to be able to, I'm going to be able to explore the data, and Gavin is going to be able to have a whole new range of instruments, some of which produce very weird sounds indeed, which is his speciality. He does weird composition. And this was a nice thing to do. We had a while playing with this. We felt it still wasn't going quite far enough, because what we're doing is we're making some assumptions. We're not listening to the universe. We're taking electromagnetic data, converting it into sound, and then listening to it. And that middle step felt clumsy. Didn't feel quite the right thing. So we thought, well, can we do something different? And we came up with something that we call the soniverse. And this is basically trying to rebuild all of the laws of physics from scratch so that instead of producing light, they produce sound. So instead of producing photons, little particles of light, we produce things we call sonons, little particles of sound. Can we rewrite all of the laws of physics to do this? And the answer is possibly. It's a lot harder than we thought it was going to be. I've had to reinvent the ether because sound needs a material to travel in. So I've had to fill the universe with an ether. Now, when I first came across that, that seemed like a bit of a fudge, and we weren't happy with that. And then it suddenly occurred to me that what I'm basically doing is filling the universe with something which is invisible, which we can't detect, and is spread out differently from the stars. In other words, I filled the universe with some sort of dark matter. And so what we're looking at now is whether we can use our ether to replace the dark matter and see what effect that has on our soniverse gravity. So this is all very esoteric in a sense. I'm interested in doing it for a number of reasons, but Gavin's interested in doing this because he thinks this is the future of music. If you look back over the last 500 or 600 years, Western music in particular has followed a very clear path, parallel with the development of mathematics. It's not connected, but they've gone in the same sort of way. So from the 1400s, where you had basically monophonic individual voices chanting, and then people started adding harmony, and you got madrigals in the Baroque period. And then the harmony began to be refined and made more complex, and Bach and Mozart and Handel started doing things like that. And then it became bigger and more complex in terms of the relationships between the harmonies. And you got Beethoven, and Wagner, and Stravinsky. And then people started adding dissonance, and they started relating that to the mathematical concepts of prime numbers. And you got people like Philip Glass and Messiaen. And in the last sort of 20 or 30 years of the 20th century, you've got people like John Cage and Trevor Wishart, who are starting to use phrases like lattice, mass, grain, and texture to describe the compositions they create. And some of them are very hard to listen to, but some of them are incredible. But the terms they're using are the mathematical terms that we were using to describe aspects of the universe at that time. But that's moved on. And now when we talk about the universe, the mathematical terms we use are things like curvature, symmetry, spin. These are the terms that we use in physics to describe the mathematics of what we're looking at. And what Gavin is interested in doing is seeing whether we can produce music which also draws on those same mathematical concepts. And that's where the Soniverse comes in. Now, this is a huge amount of work. It's very complicated. Neither of us have time to do this, if we're entirely honest, but we still want to. And the reasons are very simple. I'm interested because I want to see if we can hear astronomical phenomena. Can I hear redshift? Can I hear stars evolving? We have a big advantage when we start doing things in the Soniverse because sound travels much slower than light. And that actually means everything happens more quickly. So instead of a universe, if you tried to simulate a universe in real time, you'd have to sit around for 15 billion years. A Soniverse lasts about 25 minutes, which is much easier. So we've got ways of exploring that we didn't have before. But there's also, can we hear dark matter, dark energy? Can we hear orbits? Can I use sound as a way of exploring astronomical phenomena that goes beyond what my eyes can easily do? Gavin is interested in this as a computational tool, a new kind of instrument. So instead of writing for violin or for piano or for electric guitar, he develops a universe in the computer, sets up its fundamental principles, the strength of gravity, the nature of the ether, and so on, and then just lets it evolve and listens to it. It's also potentially a new way of playing around with the universe. So I can imagine an app for your phone where you point at different parts of the sky. Many of you probably do this. I do it because I'm hopeless at finding constellations. Point them at different parts of the sky and they tell you what you're looking at. But as well as doing that, you could hear what you're looking at, which would add another layer to it, but also might mean that these things become more useful, those with vision problems and so on. So that's another one. But the main reason is because we think we can. It's because it's there. As far as we know, nobody's ever done this, and we really, really want to. Now, we've made a start. It's very early stages. I've built a basic cosmological model, which you can play around with the fundamental parameters, the strength of gravity, the age of the universe, the amount of mass in the universe, and so on. Sorry, Soniverse. And then it produces sounds distorted by traveling through the gravity of that Soniverse. It's not all of the physics yet. We've got a long way to go, but it's a start. And already Gavin is able to use this to compose new work, but I'm also being able to use it to hear what happens when you make the universe more or less dense and where the big effects are and so on. I'm not going to go into the details of this because I get far too excited and end up talking too much, but we've got a long way to go. We've got the beginnings of the cosmological model, but what I don't have is what we call emission mechanisms. I don't have the equivalence of how atoms produce the light, the black body radiation that things produce because they glow, the quantum physics that allows us to see particular colors for particular elements and so on. I don't have that in my model yet. I'm having problems with electric charge at the moment, and I'm still working on that one. But the important thing is this isn't what we were doing with the sonification. This isn't just taking energy to frequency and turning them around. This is rebuilding the laws from the beginning. And that means that unlike light, with sound, things like amplitude and duration are important. They're not things we think about in terms of light. You don't think about the amplitude of light, but you do think about the amplitude, the volume of sound. So these are all fundamental questions that we're trying to get to grips with. It's been on hold for the last 2 years, essentially because our normal way of working is to go for a long walk together. And Gavin's in London, I'm in Merseyside, so we haven't met. But we're hoping to get back together again fairly soon and move this on to the next stage. And we're not the first people to do this. First people to do this to this extent, but scientists have and astronomers have for a very long time been trying to use sound to understand the universe better. Kepler is a very good example of this. When he was taking his measurements of the movement of the planets, he felt there should be a perfect harmony to them. He was a great believer in the perfection of the universe as God created it, as he saw it. And so he actually associated musical scales with each planet. And this is a diagram from one of his works, The Harmony of the Spheres. And what he tried to do was use the orbits of the planets and these scales to create music, to see what that music sounded like. What he found was it sounded awful. It's a cacophonous mess, and he got quite discouraged. But he was still, in a sense, doing the same sort of thing that we were, trying to find the harmonies in the underlying physics that we can then use to produce music. So to return to where I started, roughly, C.P. Snow. Back in 1959, he wrote his Two Cultures, and he had this statement, which I think is particularly important. As he saw it at the time, he saw two polar groups, two completely different groups of people. At one end, what he called the literary intellectuals, and at the other, the scientists, essentially the physical scientists. And he said, between the two, a gulf of mutual comprehension. Now, I don't know whether that was entirely true then. I certainly don't think it's true now, but there are challenges. But the reason I don't think it's true now is because actually artists and scientists are doing many of the same things. Fundamentally, we're both asking, what if? What if the universe was like this? What if the laws of physics were like this? What if I created this artwork? What does that tell me about the nature of things? And we're both doing this because we want to change how we look at our world. An artist is going to create an art because they want people to think differently after seeing that art. A scientist is looking at theories of the universe, theories of particle physics, theories of biology, because they want to change the way we look at the universe, physics, biology. And they're both using imagination. You will all know this because you know the importance of imagination to understanding the space properly. But to a lot of people, science is the opposite of imagination. But no, in order to do science properly, you have to be very imaginative because you have to ask those what if questions. But there are still differences. And I think, this is a entirely personal view, I think the difference comes from the constraints that we impose. So art is constrained by the wishes of the artist, what they want their audience, their viewer to feel, whereas science is constrained by reality. And that constraint changes the way we do things, the day-to-day practicalities. But we can still have very similar conversations because we're both fundamentally trying to do the same sort of thing. So I don't really believe there are two cultures. I think there is a breadth of what we can call culture, and people inhabit different parts of that, but they can move around and they can still talk to each other. And I'm going to keep doing this because I think it's important to share what we do. I think it's important that we try and break these perceived barriers between the two cultures, but most of all because I'm having an absolute whale of a time, and I haven't enjoyed myself so much since I started doing astronomy by bringing all this together. So thank you very much for listening. I hope I haven't gone on for too long. I tend to get a bit overly enthusiastic about that. I hope you found that interesting. I hope it stimulated a few thoughts in your heads, and I hope that you might have some questions for me. So thank you very much indeed.